Good morning. In this lecture, what we're going to do is we're going to start introducing the idea of a probability distribution. So a probability distribution is basically a function which can help to describe probabilities. So that should be an interesting idea to you because with functions, you put a number in, you get a number out. Every single time you put that same number in, you get the same number out. But probabilities have elements of randomness associated with them. So we're going to see, with that said, we're going to see how we can actually use a function, though, to describe that process. All right, so in the old days, you had functions that look something like this. F of x equals mx plus b. F of x equals ax squared plus bx plus c. So with these functions, these a little high for me. With these functions, it's clear what type of function we have. So in other words, if I just say to you, hey, I've got something that looks like mx plus b, then you know, oh yeah, that's going to be a line. Okay, the m and the b can change. The m and the b are parameters, but something with this structure is linear. Similarly, something with this structure, ax squared plus bx plus c, is going to be quadratic, assuming that a is not equal to 0. So if I tell you, hey, I've got something that looks like this, then a, b, and c are parameters once again, but you know that this describes a quadratic function. So now I'm going to introduce another way of describing a type of function, in particular a function known as a probability mass function, to help us describe probabilistic events. And the definition is just a little bit more high-tech than what we're seeing here. So here's the definition of a Pmf, or a probability mass function. So a Pmf, so probability mass function, and that'll probably be one of the last times you hear me say probability mass function. I'm going to say Pmf for a discrete random variable capital X, we'll talk about that in a second, is a function with the following properties. So first off, f of little x has to be greater than 0 for all x in the sample space. So the outputs of my function have to be positive. 2, if I sum over all x's in the sample space, then I get 1. Third, the probability that a particular x value is in a particular subset can be found by adding up all of my functional values within that set. So all of this stuff together is the same thing as me saying, hey, it's a linear function if it looks like mx plus b and m and b are real numbers. Okay, so it's the same idea, but a lot more high-tech. So let's talk about this. So a probability mass function for a discrete random variable. So you may need to review this, but way back when in the first lecture, I talked about different types of sample spaces. I talked about discrete and continuous. So we're going to be talking about discrete random variables over the next several lectures, then we'll dive into continuous. So discrete random variable capital X. So capital X, or boldface X, is representing some sort of process which has no definite outcome. So for example, capital X could be the number of dots on a die when you roll a dice, or when you roll a die. Okay, so it's representing something that has randomness associated with it. Okay, so this is going to be a function with the following properties. So f of little x, so when I talk about little x here, little x are the specific values that I'm putting in. So for example, here, this is representing the whole process, but little x could be 1 or little x could be 2. That's an example. So as I said, the output has to be positive. Okay, that makes sense to me because we're dealing with probabilities. The sum of the little f of x's over all x's in the sample space has to be 1. That also makes sense to me because, or I wouldn't be surprised if it's in the definition because we've talked about that. If you sum up the probabilities, then over a whole sample space you should get 1. And finally, the probability that x is in a particular subset can be found just by adding up those probabilities. So in the die example, if I want to know the probability that x is contained in 1 or 2, in that subset 1 or 2, this is saying I can just add up my f of x to get that. Okay, well, what is, I haven't described what the f of x is, but what is this probability? Well, this will just be 2/6. This will just be 2/6. And it turns out, so this we know just from without this stuff, it turns out that in this situation, and I'm going to write it out explicitly in just a minute, in this situation, the PMF that describes this situation happens to be 1/6. And it makes sense because, if I have any subset here and I want to know the total probability, so 1, 2, or 4, 1, 2, or 5, 1, 2, or 6, how am I going to actually get the probability? Well, the only way for me to get the probability is for me to add up 1/6 that many times. So that's what this is describing. Okay, again, I'll get back to that in, actually no, let me do that right now. So this situation is an example of a particular PMF known as the uniform distribution. So just like we have linear functions, quadratic functions, in the world of probability, we have different distributions that model different types of events. And the uniform distribution is the function, the probability mass function, or the PMF, that describes a situation where you have a discrete set of outcomes, and those outcomes go from 1 to m, and each of those events are equally likely. When that's the case, the PMF is given by f of x equals 1 over m, and this is for x equals 1, 2, 3, up through m. So with the die example, if big X is the number of dots on a single row, f of x equals 1 over 6, for x equals 1, 2, up through 6. I guess I could have written 3, 4, 5. That seems really, really lazy. I'm going to do that. X equals 1, 2, 3, 4, 5, or 6. This is the outcome space. So again, this guy's positive. Okay. If I sum them up over the sample space, I do get 1, 1/6 plus 1/6 plus 1/6, et cetera, 6 of those guys. And as we talked about up here, to get the probability that x is in a particular subset, we just need to add each of those guys up. Okay, so one other thing that I want to talk about is that instead of this little f of x notation, a lot of times we're going to use this notation. So the probability that big X equals little x is the same thing as f of x. So this big X business, I know from personal experience and from teaching this for a long time, it's a little bit confusing at first. You just have to remember that the big X is representing the process. So as an example, hey, what's the probability that this random number of dots is equal to 2? So that's the same exact thing as f of 2, which is the same thing as 1/6. So that's just a bit of notation. All right, so that's the first PMF. I want to introduce a second PMF. And again, over the next several lectures, we're going to be looking at different functions that can represent different types of probabilistic events. So this next one is called the Hypergeometric distribution. And we're going to find this formula through an example. So let's say 12 students who identified themselves as boys and 13 students who identified themselves as girls. Let's say they're sitting in a room. Okay, 7 people are chosen without replacement. My goal is to find the following. I want to know what the probability that X of them are boys. So the random thing that I'm looking at here are the number of boys. Okay, so I choose 7 at random. I want to know what the probability of that that X of them are boys. So what I want you to do first, this is our main objective, but what I want you to do first is pause the video and see if you can come up with the probability that big X equals 1. Hint, this is a combinations question. Okay, so hopefully you gave that a shot. Let's see, out of the 25, I'm choosing 7 people. From the 12 boys, I'm choosing 1 of them. And then from the 13 girls, I'm choosing 6 of them. So that's what f of 1 should look like. F of x, then, is what? So I want to derive the generalized function based on this process. So again, pause the video, give that a shot. And I actually want 2 things. I want the function and I want the sample space. So give that a shot. All right, hopefully you gave it a shot. Well, let's see. From the 25 students, 25 people, I'm still going to choose 7, regardless of this, right? That's not going to change. But from the 12 boys, I'm going to choose X of them. And from the 13 girls, I'm going to choose, let's see, I'm choosing 7 total. So I guess 7 minus X over here. And the number of boys could be 0, 1, 2, 3, 4, 5, 6, or 7. Okay, I can't choose 8 boys because I'm only choosing 7 people total. All right, so you actually just came up with a hypergeometric distribution. And there's a fancy formula for this. I'm going to write this formula down because we're going to need it in a subsequent proof. But here's another example where, quite frankly, I wouldn't bother memorizing the formula. I would not memorize this formula. We just need it for a future derivation. This, to me, is just a combinations question. And in fact, several of these types of PMFs, or probability mass functions, or just like the Bayes theorem, the Bayes rule, can be found just by our understanding of the basic probability concepts that we looked at, as opposed to trying to memorizing something. So let's see what we did, though, and come up with the formula in general. So in general, what does the hypergeometric distribution model? So if you have 2 classes of things, so let me say we have these two classes. We have big N1 of the first group and big N2 of the second group. So here we have boys and girls. We choose N without replacement. And let's let big X be the number from N1. So well, let me not say N1. Let me say from group 1. So I want to know the probability that big X equals little x. Okay, so give that a shot. Pause the video, see if you can come up with the abstract version. It's the same process. Right, hopefully you try that. And let's see. We've got a total of big N, and I'm choosing little n from that. From the big N1, I'm going to choose x of them. From the big N2, I'm going to choose little n minus x of them. Right, so again, here little n was 7. Okay, that matches up. Big N1, big N2, awesome. Big N, little n. Big N is big N1 plus big N2. So that looks like the PMF. Little x better be less than or equal to little n, right? Because we're not going to pick more than the n that we're choosing. Little x has to be less than or equal to big N1, right? You can't choose 18 boys from 12 of them. And finally, n minus x should be less than or equal to big N2. All right, so in today's lecture, I introduced the idea of the PMF, the probability mass function. We looked at a couple of examples of actual probability mass functions and what they can model. The main ideas of the probability mass function is that the function itself is a probability. And when you sum the probability mass function over the sample space, you're going to get 1. That's all for today, and I hope you enjoyed the lecture, and I will see you next time. Thanks so much.